Now in this session we are going to see the wave nature of particles in quantum mechanics in module 4. Now let us see the introduction to quantum mechanics. What is a black body? A body which absorbs all the radiations that are incident on it, and on heating it emits all the radiations that are being absorbed by it. This is called as a black body. So absorption coefficient is 100%, and when it is heated to a particular temperature, it emits all the radiations that are incident on it. For example, hot filament or a sun may be approximated as a black body. The German scientists Rayleigh and Jeans investigated the energy emitted at different wavelengths at various temperatures, but they were successful only at a longer wavelength. And scientist Wayne could explain only at a shorter wavelength. So, Rayleigh and Jeans could not explain at shorter wavelength, whereas Wayne could not explain at a longer wavelength. But Max Planck realized that energy of emitted radiation is quantized, and he gave an equation for energy density for a black body radiations. And he said that quantization of energy led to the quantum mechanics. Now you can see the diagram over here. The black body radiations, when the body is heated different temperatures, you can see the distribution of energy in this graph. For different temperatures, the energy of radiation is been different. So, when the body is heated to 5000 Kelvin, the distribution of the curve is like this. When the body is heated to 4000 Kelvin, the distribution is in this way. And the body is heated to 3000 Kelvin, the distribution is in this way. You can see that there are different curves for different temperatures. For different temperatures of black body, there are different curves. And also at a given temperature, the energy is not uniformly distributed in the radiation spectrum. That means at a given temperature, it is increasing, intensity increases and again decreases. It is not uniform. So this is what at different temperatures you can see the energy is not uniformly distributed. At a given temperature, the intensity of radiation increases in wavelength lambda maximum. Its value is maximum. You can see here, as the temperature increases, the lambda maximum corresponding maximum wavelength is 0.5. For 4000 Kelvin, the maximum is approximately 7, and for 3000 Kelvin, it is at 1. So, as the temperature increases, lambda corresponding to maximum wavelength is decreasing. As the temperature increases, the lambda maximum is decreasing. That is what is being said. And the wavelength for which the radiant energy is maximum. Lambda maximum decreases as the temperature increases. And here you can see at a given temperature, the intensity of radiation increases, its value is maximum, and again further decreases. You can see here, intensity initially increases, reaches maximum, and again keeps on decreases. This is the energy distribution by a black body. This Max Planck could explain at both shorter wavelength as well as the longer wavelength. This is the distribution of energy of a black body for different temperatures. Now here Max Planck has given assumptions. The value of energy could be possessed by an oscillator is an integral multiple of h nu, where h is a Planck's constant and nu is the frequency. The value could be possessed by an integral multiple of h nu. E is equal to h nu. And also he has given this equation called as a Planck's radiation law. It is u lambda d lambda is equal to 8 pi hc by lambda to the power of 5 into 1 by e to the power of h nu by kt minus 1 into d lambda. This is a Planck's radiation law, where h is a Planck's constant, c is the velocity of light, and t is the absolute temperature, lambda is the wavelength, and k is the Boltzmann constant. This is the Planck's radiation law, which could explain the black body radiations at longer as well as a shorter wavelength. Now we see with the nature of the particles. De Broglie hypothesis. What does a de Broglie mention? What does a de Broglie says? By the law of symmetry of nature, particle exhibits wave properties in addition to the particle properties. That means waves are waves. You know that light waves. Light is a form of wave. Light exhibits wave nature as well as a particle nature. Similarly, de Broglie has said that when the law of symmetry of nature, the particle exhibits wave properties in addition to the particle properties. So what is the dual nature of light? Matter is made up of particles like electrons, protons and neutrons. Also, waves are associated with these matter particles under suitable conditions. Thus, matter exhibiting both particle and wave nature is called as a dual nature of matter. De Broglie waves are the waves associated with the material particle in motion. for a particle of mass m moving with a velocity v. Here what does the de Broglie says is, every moving particle is associated with a wave having a wavelength of lambda is equal to h by p. Every moving particle which is having a velocity, every moving particle is associated with a wave having a wavelength of lambda is equal to h by p. P is equal to momentum, mass into velocity. So de Broglie has said that the waves associated with the material particles in motion for particle of mass m moving with a velocity v has a wavelength of lambda is equal to h by mv or h by p. Next we see the de Broglie wavelength of electron. De Broglie wavelength of electron accelerated in a potential difference of v volt. The kinetic energy of electron of mass m charge E accelerated to a potential of v. Here we can say that half mv square kinetic energy is equal to E into V. V is the voltage applied and E is the charge of electron. So half mv square is equal to E into V. Multiply and divide by m. Here m square V square can be taken as P square. So here we take it as P square is equal to 2m EV. 2m EV. Here m square V square is nothing but P square is equal to 2m EV. Or P is equal to root of 2m EV. We know that mass into velocity is nothing but P. So here we are taking lambda is equal to h by P. P is equal to root of 2m EV. From this equation we are substituting the value of P into this. Putting the values of h value, mass of electron as 9.1 into 10 to the power of minus 31 and charge is 1.6 into 10 to the power of minus 19 into V. Substituting all these values, you will be getting as lambda is equal to 1.228 nanometer by root V. V is the potential, or it can be mentioned in terms of a angstrom. It is 12.28 by root V angstrom. So here it is lambda is equal to 12.28 by root V in terms of angstrom. This is the de Broglie wavelength of an electron. Now what is the relation between kinetic energy and the de Broglie wavelength? Here we have seen that since kinetic energy of an electron is equal to half mv square, also energy of an electron accelerated under a potential difference of v is E is equal to E into V. Also we know that lambda is equal to h by P. From h by root of 2m EV, we know that EV, from here EV is equal to capital E, so lambda is equal to h by root of 2m E. So this is the relation between the kinetic energy and the de Broglie wavelength. Lambda is called as a de Broglie wavelength and kinetic energy is half mv square. So here directly you can substitute the value of, you can get the value of wavelength if you know the energy of an electron. If kinetic energy of an electron E is given, or if energy of an electron is given, directly substitute in this value in this formula to get the de Broglie wavelength. Thank you.